All right, this is Mr. Jern, and I am going to show you how to resolve vectors into their x and y components. So you have a vector, in this case it is 2.5 newtons, it's a force, to the north and 50 degrees to the west. Okay, so the first thing you want to do with this vector is to draw the vector in the general direction. So I know that I'm going to have a vector going to the north and to the west. And so what I'm going to do is I'm just going to again, it doesn't have to be perfect. I'm going to draw something to the north and to the west. To help me out with that, I'm going to first draw my compass rose. In other words, north, never eat soggy waffles, right? North, east, south, and west. That's going to help me to just remember and keep the directions straight in my head as I go forward with this. So north and to the west is going to be a vector that basically goes like this. And it doesn't really matter exactly how we do it. In fact, let me redraw that a little bit. It doesn't have to be perfect or anything. It just needs to be in the general direction, north and to the west in our case. So north and to the west, just like that. Okay, so that's it. So now we have something to work with, and it's just something to visualize it. If you were drawing it and trying to be accurate, you wouldn't just do it like that. So now we're going to draw the right triangle in the given order. And again, the given order just means, in our case, we're going to go north and then to the west. So we're going to actually break up this vector by going north. So there's our one component, and we're going to go to the west after that. So there's the second vector. Again, they're just representations to help us out. Third, we're going to label the angle. The angle is going to be given, it's going to be where you started from. This is why it's important that you go in the given order. So you know that this right here is going to be our theta. This is going to be our angle, okay? And you know that because you went north and then west. It would have been, if you didn't go north and west, it would have been something, it would have been the other corner. But so we're just going to stick with the angle there. Now we're going to label the vector, the x and y components, and the triangle sides. Our vector in this case is going to be the first arrow we drew, 2.5 newtons. You could label it as F if you want to, because newtons does indicate that it's a force. But I'm just going to label it because we already know what it is. It's 2.5 newtons. The vertical component is always going to be the y component of that vector, because just like in a graph, vertical means y. So this is going to be my force in the y direction, and this will be my force in the x direction, the horizontal part. That's always going to be the case. Horizontal will always be x, vertical will always be y, just like with a graph. Now I also want to label my triangle sides, because we're going to be using triangles to help us solve this. So my hypotenuse is this one right here. The side that's opposite of my angle is going to be this one, and my side that's adjacent to my angle will be this one. And once again, we're just using the triangles to help us solve this vector and resolve it into its components. So everything's labeled, so now I'm going to list the givens and the unknowns. So in this case, I like to, and just in all cases for these things, I like to start with the angle, since that's the most obvious thing we know. So the angle, the theta, in this case is going to be 50 degrees. I just got that from right here. Okay, nice and easy. In this case, we have a force, and so the force is going to be our hypotenuse. So I'm going to start equating these to the triangle that we drew, and that is going to be 2.5 newtons. Okay, so that's a given. And now I want to get into the components. I'm going to start with f of x. Doesn't really matter which one you do first. It doesn't, as long as you get this next part correct. The f of x is going to be my opposite side. Okay, I'm just going to write OP so I know it's not a 0. And that is going to be one of my unknowns. The other one, fy, is going to be the adjacent side of this triangle from where we drew earlier. And again, you got to get this part right. And that is going to be the other unknown. Done. We listed the givens and the unknown. Now I'm going to use the equations, substitute, and solve. So this part's pretty straightforward because these equations are based off of the SOHCAHTOA equations. And the first one is just going to be SO. If you remember, SO is sine of theta is equal to the opposite over adjacent. So this is just a standard equation, SOHCAHTOA. It's also, so to show you, we rearrange that, and this equation is always going to be the same. The opposite side will be equal to the hypotenuse times the sine of theta every single time. Now I'm leaving room because I'm also going to do the same thing for the adjacent side, but I'm just going to, for now, carry on. Now I'm going to substitute. So the opposite side, again, this is not a 0, this is opposite. So I look at my list, and my opposite side is going to be, or it is, because I already defined it, f of x. And that's going to be, not f of x, I apologize, the force in the x direction, fx. And that is going to be equal to the hypotenuse. I'm going to put this in parentheses, and the hypotenuse we've already defined as 2.5 newtons times the sine of theta, which we said is 50 degrees. Okay, that's my substitution. And now I'm going to solve it. And I just want to make sure that we are we're okay so far. So the thing we've done so far now, or up to this point, is just it's pretty standard. And now we plug it into our calculator, as you should know how to do by now. And when we do that, we find out that F in the x direction, or the x component of our force, if you want to call it like that, which is accurate, will be, I'm just going to round it to 1.9 newtons. And like our last step, we got to include the magnitude unit and the direction. So I'm going to put the direction. And in this case, it's the x direction. And if I look back here, it's going to be either north or it's going to be to the west. In this case, it is going to be to the west because that is the x direction. Okay. So now I get to go back and basically do that again for the adjacent side. So I'm just going to separate that out just to kind of keep things neat. Oh, speaking of keeping things neat, I should put a box around my final answer, okay, because that is the final answer, and I want to make sure it is noticeable. So now the other one, the next equation is always also going to be the same, and this one is the adjacent side is equal to the hypotenuse times the cosine of theta. Okay, we got that one from the other equation. Let's see, that would be, right here. Cosine, this is just cosine of theta, is equal to a over h. So that's ka from SOHCAHTOA. So these two equations up here give us the two equations that we're always going to be using down here. They're just rearranged versions of those. So once again, substitute and solve. So in this case, A is going to be our Fy. So Fy is equal to our hypotenuse, which is 2.5 newtons again, and times the cosine of theta, which is 50 degrees. And when we solve that in our calculator, we get Fy, force in the y direction, or the y component of our vector, will be 1.6 newtons to the north, because that's the other direction. That's the direction in the y, that's the y direction. So that is it. We have solved our vector. We resolved it, I should say, into its x and y components. And from this point out, we will be able to use them however we want. Goodbye.